Bismillahirrahmanirrahim. In this video, we'll talk about symmetrical faults and we'll solve two examples. So let's see what is a fault. A fault in a circuit is any failure which interferes with the normal flow of current. Most faults on transmission lines of 115 kV or higher are caused by lightning, which results in flashover of the insulators. And what is flashover? You see these insulators, they have just been short-circuited. A flashover, a high voltage electric short circuit made through the air between the exposed conductors. Now there are two types of faults, symmetrical faults and unsymmetrical faults. A symmetrical fault involves all the three lines, so they are all shorted or the three lines shorted with ground. So this is the symmetrical fault. Whereas unsymmetrical fault will be a fault between any two lines, or any two lines or ground, or any two lines like this. So it is even line to ground fault, line to line fault, and this is line to line and ground fault. Whereas the upper one was line to line, and this is line and ground. So roughly 5% of all faults involve the three-phase faults, and remaining 95 are the unsymmetrical faults. Okay, now when there is a lightning strikes the lines, three phenomena that occurs. Immediately after the strike, we get a subtransient envelope, and then this gradually dies down or reduces to what we say the transient period. This is the subtransient period, and then this is the transient period, and gradually it normalizes to steady state. Now the current flowing in the lines were AC, but the lightning strikes induces a DC voltage in this, and so is this envelope is because of the induction of high DC voltage in this. So the subtransient period, the first cycle or so after the fault, AC current is very large and falls rapidly. The transient period is current falls at a slower rate, so from like here to here. And the steady state, when the current reaches its steady state value. Note that before the fault, only AC voltage and currents were present with the generator, but immediately after the fault, both AC and DC are present. So this DC component is introduced because of the lightning. Now the current, voltage and time constant, reactance, etc. are denoted by double comma, single comma, and no comma for subtransient, transient, and steady state periods. And for example, the subtransient reactance is given by this double dash, transient reaction is by single dash, and steady state reaction by no dash, nothing. Okay, some background. The transient analysis of synchronous generators required two axis machine models, and we have seen that corresponding equations involve the physical ABC phase, we know, and this can be simplified by a transformation by Mr. Parks, which introduced DQN zero axis, that is the direct axis, quadrature axis, and zero sequence, and that is applicable to currents, voltages, and flux, etc. And that is why you will see The subtransient reactance is X double dash, and this D symbol representing that it is a direct axis. We are talking of direct axis. And similarly, single dash with D represent the transient reactance with direct axis. Now let's see the equivalent circuit for synchronous generators. For subtransient period, it will be, the voltage will be represented by this double dash, and same is the reactance. For transient period, it will be with the single dash, and for synchronous reactance or synchronous period or steady state period, there will be no dash. Note that these values are actually given by the values of the reactance are given by the manufacturer. And here is an example. The manufacturer has given that XD is 1 and XQ. Now this is the quadrature component. Is this value X single dash D is 0.3 and X double dash D is 0.2. So we use these values in the calculations. At this point, it is important to note that the particular value of voltage in series with the reactance XD, so X double dash G and X double dash DG represents the generator immediately before and immediately after. So for both pre-fault and after fault, we use this model. Okay, now let's discuss the internal voltages of a loaded machine under fault. So this is the machine and this is a load connected, and to simulate a fault like this fault, what we have done is we have used a switch here. So when switch is connected, that means a fault has occurred, and when a switch is not connected, then this is a normal circuit. And this is only one phase representing single phase equivalent of the three-phase circuit. So before fault, now we have, instead of load, we have incorporated the motor here. So motor voltage or motor is also when there is no supply and when this will be short circuited, the motor will behave like a generator, and that is why we are representing it by EM double dash and the motor reactance, and this is the generator reactance, and this is the reactance of the load line or the transmission line. So when the fault occurs, we close this switch, and so this is the condition. Now there will be two circuits, one is through this and other is through this. And now you can see this is now the short circuit current or the transient subtransient current for the generator IG. This is the subtransient current for the motor, and sum of the two will be the fault current IF double dash. Now let's do an example. The synchronous generator and motors, they are rated to this, have the subtransient reactance 20%. Line connecting them have a reactance of 10%. The motor is drawing this much wattage and 0.8 power factor and has a terminal voltage of 12.8. When a symmetrical three-phase fault occurs at the motor terminal, find the subtransient currents in the generator, the motor and the fault by using internal voltage of the machines. Note that the generally kVA, kW given in questions are for three-phase. Also kV is for line to line. So this is for three-phase and this is for line to line. Same, this power is for three-phase and this is also for line to line. So these are the parameters for the generators. These are the generator components. This is similarly the rating of the motor along with the power consumption and the terminal voltage. So the first point is that calculate the parameters for single phase. So I prefer this to do for the single phase, but in the book they have done it with the three phase. Doesn't matter. Okay, so the base, first let's calculate the base parameters. So generator base, this will be taken as the base. So generator base for three phase was 300 kVA and the base voltage is V line to line 13.2. From here we convert that into single phase. So kVA divided by 3 will give the single phase kVA rating, and the voltage now line to neutral instead of line to line, we can get it by dividing this by under root 3. So it is 7.621 kV. And from here now we can calculate the base current. So S single phase divided by V phase, we get this equation. Now let's see the motor parameters. The power consumption for three phase and the terminal voltage for three phase 12.8. I prefer to convert these also into single phase. So the power consumption per phase divided by 3. So this is the power consumption, and the line to neutral terminal voltage will be divided by under root 3, 7.39. 12.8 divided by under root 3. So now we have got the single phase parameters. Okay, so we were here, we had got the single phase parameters. Now our step number 2 will be to calculate the load current and the voltage Vf. So the load current through the circuit IL and the voltage Vf, the voltage at the fault point. And why we need IL and Vf? Because we want to calculate Eg and Em first of all. Now to calculate the load current, we know that the current is VA divided by V, or in our case would be KVA divided by KV. Now our load power is in watts, so let's convert that into kVA so it becomes easy. So the motor kVA, we divided kilowatt by power factor, so 666, this was the kilowatt divided by power factor. So this is now in kVA, and now we can easily divide it by the terminal voltage for single phase to get the current. So I load, the magnitude of I load will be motor kVA, which we have got here, and motor kV per phase, which is 7.39. So dividing this, we get the magnitude of the load current to be 1128 ampere. Now, important point, since the power factor is 0.8 leading, this means that the current is leading by theta, where theta is cos inverse of 0.8, that is 36.9 degree. So the magnitude and phase of the current, we can write it as 1128 and this angle 36.9. So this is our load current, and we can convert that into per unit. So dividing it by the base was 1312. So we get this result in per unit. And the terminal voltage Vf we can write is the terminal voltage of the motor, which was single phase 7.39, divided by the base voltage we had calculated from here. This is the base, so we'll use the base 7.621, so it is 0.97 angle 0 per unit. Okay, so we had found the load current and the VF and per unit. And we have to keep in mind that we need to find the subtransient currents of the generator, motor and the fault current. So this was the circuit. Now we need to find these two voltages, and for that we'll for the generator we'll use KVL. So starting from here, minus EG, then plus IL with these two, and plus VF, which is 0.9. So these are all in PU, and from here we can find the answer to be 0.814 plus J 0.227 per unit. So this is the generator voltage. And similarly, motor voltage, we go from here, so minus EM and I into this current and VF. So, and since the current IL is coming from the top, therefore it will be positive here and negative here. That is why we have to use a negative sign here. So negative IL J2 and plus this voltage. And so we found EM in per unit also. So now we have everything in per unit. The generator voltages, motor voltage and all the loads are given. So now we are ready to find the currents. So I generator, IG, which is this current now, we can find from the total voltage, the generator voltage, divided by the total impedance. So total impedance is sum of these two. So this is the IG double dash, or the generator transient current. Similarly, we find the motor current, EM divided by, this is the only impedance. So the motor transient current, sub-transient current, and sum of these two will give us the fault current. So we just add. So this is how we calculate the fault current. And now this was in PU. If you want to find it in into the terms of ampere or the actual, so we multiply it by the base current. So this is the current or the fault current in terms of amperes. Now this calculation helps in actually inserting the circuit breaker. Now we know the magnitude of the fault current, so we can select circuit breakers of appropriate rating. Now those who are keen to understand how it has been done in the book, you can just go through this. I have tried to explain how he has arrived into this solution and how he has used this parameter. Now let's discuss another technique, which is the Thevenin's equivalent technique for solving this problem. So if you recall, this was the circuit, and we had found out the VF, the fault voltage. Now if we insert a voltage source whose magnitude is equal to the fault voltage and whose polarity is such that the current flows in the same direction as it was flowing here, so that is why we have put negative at the top and positive at the bottom. So the current flows like this through the circuit. Then we can replace these sources here. So we can replace the voltage sources of a generator source and the motor voltage source, and we can just replace it by a fault voltage source. And so from here now we can find the total current easily. So this voltage divided by these two impedances will give you the generator fault current, and from this side it is the motor fault current, and the summation is the total fault current. Okay, now this circuit can be rearranged like this, and it can be further simplified. These two are in series and with parallel with this, so we can further simplify it like this. Remember here the positive terminal is the top, because we want to ensure that the current flows in the same direction. And we have incorporated a switch to simulate the fault. So, as you know, for Thevenin's we need to calculate the Thevenin's equivalent resistance. So we shorten the voltage source and we look from this point. So the R Thevenin is the parallel of these two branches. So we find Z Thevenin, which is the parallel of these two branches. And so our Thevenin equivalent circuit will now be this, the voltage source Vf and Z Thevenin. And to simulate, now we short circuit this terminal to calculate the fault current. So fault current will be Vf over Z Thevenin, and putting the values you get this term. So example 10.2, it says solve the example 10.1 by using Thevenin's theorem. So this was the original circuit, single phase diagram. These were the parameters we had calculated for single phase, for the generator and motor. This is the Thevenin equivalent circuit. And Vf we had already discussed that this is how we found the Vf in the previous example. So it is 0.97 J0. We have now shortened this to find Z Thevenin. So Z Thevenin is the parallel of these two. Now we are incorporating the values. So Z Thevenin is 0.12 per unit. So this is our Thevenin equivalent. We have the voltage and we have the impedance in per units. So the current through this, fault current, is just voltage divided by impedance, Vf divided by impedance. So the fault current is J 8.08 per unit, which is the same that we found out in example 10.1. And now recall that in the question 10.1 we were asked to find the current in the generator and the motor and the fault current. So we have found the fault current, which is this value given here. Now by current division rule we can find the other two. So this was the equivalent circuit. This is the motor fault current and this is generator fault current. So the generator fault current is the total current, which is here, divided by total impedance and multiplied by opposite arm. So this is generator's opposite arm is 0.2, and similarly for the motor, same procedure, opposite arm in this case is 0.3. So these are the two values in terms of per unit. Now if you want to include the load current, which sometimes is neglected, but we had found the load current in the example 10.1. This was the load current per unit. So we just add in the generator and subtract from the motor, because in the motor the direction was opposite. And so we get this these two subtransient currents. And now if you these are the per unit values. It is the same as we found in example 10.1. In case you want to find the values in amperes, then you have to multiply their magnitudes by the base current to find their values in the amperes. So I hope this gives you an idea as to how to solve this type of a problem. Thank you.